Welcome to the deep dive. Today, our mission is pretty specific. We're diving deep into just one chapter. Chapter 4 of the Feynman Lectures on Physics, Volume 3, the topic, Identical Particles.
And this is where quantum mechanics really stops being just equations and starts showing us something deeply weird, something fundamental about nature itself.
Okay, yeah, the idea that when particles are truly identical, like two electrons, they aren't just really similar, they're completely, utterly indistinguishable.
Exactly. You literally cannot tell them apart, ever. And that simple fact has consequences that are, well, completely impossible in the classical world we experience every day.
So classically, you could imagine, I don't know, putting a tiny scratch on one coin, even if they looked identical, and tracking it. But quantum mechanically, no way.
No, that kind of tracking is forbidden if they're truly identical, and that impossibility dictates how they interact. Feynman uses this great example. Imagine scattering two identical particles, call them Allen and dollars.
Right, and they end up in two detectors, say detector 1 and detector 2.
Classically, you'd think, okay, either a dollar went to 1 and a ball went to 2, or Ada went to 2 and Bola went to 1. You'd figure out the probability for each path separately.
But because they're identical, you can't separate those paths. You can't know which particle did which. Both possibilities lead to the same final state.
Yeah.
One particle in detector 1, one in detector 2.
And that is the absolute crucial quantum step. You don't add the probabilities, you have to add the quantum mechanical amplitudes for each indistinguishable process first.
Ah, and adding amplitudes. That always means interference, right?
Always. That's where the quantum weirdness comes in. So you have the amplitude for the direct process, say we're at 1, b to 2, 2, and the amplitude to the exchange process, a to 2, b to 1 on. The total amplitude is the sum.
But how do they sum? Feynman points out there's a phase factor involved when you swap them.
Exactly. When you exchange the rolls of an A and of dollars, the amplitude for that exchange process is related to the original amplitude by some phase factor. Now, here's the key constraint. If you exchange them twice, you have to get back to the exact same physical state you started with.
Okay, so swapping a dollar in dollars and then swapping them back again, that changes nothing overall.
Right. Mathematically, that means this phase factor, when squared, must equal 1.
And the only numbers that square to 1 are +1 and -1.
Bingo. That simple physical requirement forces this phase factor to be either plus epsilon or 1/1. And this single choice, this sign difference, divides literally all particles in the universe into two fundamental families.
Okay, let's define those families based on that sign. What if the sign is positive?
If the total amplitude is amplitude direct plus amplitude exchanged, meaning they interfere with the same sign, we call those Bose particles or bosons.
They add up constructive interference, like they're encouraging each other?
You could think of it that way, yeah. Bosons are kind of the social particles. Examples include photons, particles of light, and also composite things like alpha particles. And a key feature Feynman mentions is they tend to have integer spin, 0, 1, 2, and so on.
And the other choice, the minus sign.
If the total amplitude is amplitude direct minus amplitude exchanged, they interfere with the opposite sign, destructively. These are the Fermi particles, or fermions.
Okay, and who belongs to this family?
These are basically the particles of matter as we know it. Electrons, protons, neutrons, they're all fermions. And they typically have half-integer spin, like 12, 32, etc.
It's fascinating, though, that composite particles follow this, too. You mentioned alpha particles are made of 2 protons and 2 neutrons, right? All fermions.
Yep, 4 fermions in total.
But the alpha particle itself behaves like a boson. How does that work?
Because the rule applies to the total spin of the entire particle system. Even though it's made of things with half-integer spin, the way those 4 spins combine in an alpha particle results in a total spin that's an integer. So the composite object, the alpha particle as a whole, obeys Bose statistics.
The identity rule looks at the whole package deal.
Exactly, it's holistic.
Okay, so we have these two families defined by a plus or a minus sign. Let's explore the consequences, starting with the bosons and their positive sign. You call them social. How does that play out when you have lots of them?
Right, this leads to something called Bose enhancement. It comes directly from that constructive interference, the adding up. Imagine you have, say, non-identical bosons already in some particular quantum state.
Like non-photons, all with the same energy and direction.
Precisely. Now, what's the probability of getting one more boson, the done plus 1, 1, into that exact same state? Because you have to sum the amplitudes for all possible ways this could happen, including swapping the new particle with any of the dollars already there. The math shows something remarkable.
Okay, what's the result?
The probability is enhanced. It's actually none plus 1 times greater than the probability would be if that state were completely empty.
Wait, say that again. Having particles there makes it none plus 1 times more likely for another one to join.
Exactly. The more bosons you have in a state, the stronger the invitation for another identical boson to join them. They love to clump together in the same state.
Wow. So they're not just indifferent, they actively encourage piling up.
That's a great way to put it. Cooperative is the word Feynman might use.
And photons are bosons. This must be critical for light, right? For how light is made and absorbed.
Absolutely fundamental. Feynman explains that the amplitude for emitting another photon into a state that already contains dolem photons is proportional to the square root of n plus $1.
Square root of n plus $1 for emission.
And the amplitude for absorbing a photon from that state is proportional to the square root of just $1.
Okay, the square root of dollars for absorption makes sense. That's stimulated absorption. More photons present, higher chance of one being absorbed. But that square root of n plus $1 for emission, if they is 0, if there are no photons there, the amplitude is proportional to the square root of 1. It's not 0.
Exactly. That plus 1 under the square root is responsible for spontaneous emission. An atom can emit a photon even into an empty state. But once you have nully photons present, that emission probability gets boosted by the existing photons. That's stimulated emission.
The principle behind lasers.
Precisely. Lasers work because of the cooperative nature of bosons.
And this Bose enhancement, this tendency to pile up, connects directly to blackbody radiation, doesn't it? One of the big mysteries that kick-started quantum theory.
It's the whole explanation. If you consider photons in a hot cavity, like inside an oven, they're bosons in thermal equilibrium with the walls. Their cooperative nature dictates how many photons you'll find at each energy level, or frequency.
So you calculate the average number of photons in a given state at a certain temperature.
And because they are bosons obeying this 1 plus 1 enhancement rule, the math leads directly to the formula B equals 1 over eta to the power of Caramego U5O minus 1, that famous formula.
That minus 1 in the denominator, that's the Bose statistic signature.
It is. It comes directly from the plus sign interference rule. Then you just combine that average number, $, with the number of possible light wave modes you can fit in the cavity, which depends on geometry, volume, frequency squared.
And out pops Planck's law for the blackbody spectrum, the exact color distribution of glowing hot objects.
Exactly. Blackbody radiation is fundamentally a consequence of photons being bosons. The plus sign dictates the thermal glow of the universe.
That's incredible. Okay, let's switch gears. What about the other side, the fermions, with their minus sign, if bosons are cooperative?
Fermions are the opposite. They're exclusive. That minus sign leads straight to one of the most important rules in physics, the Pauli Exclusion Principle.
How does the subtraction lead to exclusion?
It's beautiful, really. It's just mathematical cancellation. Imagine you try to force two identical fermions, say 2 electrons with the exact same spin, into the very same quantum state. Same energy, same momentum, same spin orientation.
Okay, trying to put them in the same metaphorical seat.
Right. The amplitude for the direct arrangement, electron A in state X, electron B in state X, is, well, some value. But because they're in the same state, the exchanged arrangement, electron B in state X, electron A in state X, looks identical. The amplitude for the exchange process is exactly the same as the direct one.
Ah, and for fermions, the total amplitude is the direct amplitude minus the exchanged amplitude.
So you get amplitude 0, the total amplitude is 0. The probability of that state occurring is 0 squared, which is 0.
It's impossible.
It's absolutely forbidden by the rules of quantum mechanics for identical fermions. Two identical fermions cannot occupy the same quantum state. It's not some extra rule added on. It's a direct result of them being identical and having that minus sign when you swap them.
And this principle, this exclusion, it's basically responsible for all of chemistry and the structure of matter, isn't it?
Pretty much. If electrons being fermions didn't obey exclusion, they'd all just pile into the lowest energy state around the nucleus.
Atoms wouldn't have shells. They'd all be tiny points, chemically identical.
Exactly. Hydrogen would behave like uranium. There'd be no periodic table, no complex molecules, no solids, no liquids. Probably no life. The exclusion principle forces electrons into higher and higher energy levels, filling up distinct quantum states or shells.
It creates structure, volume, stability.
That's why you can't walk through a wall. The electrons in the wall and the electrons in your body are all fermions obeying exclusion, resisting being in the same state, the same place. It's the minus sign made solid.
Does it play a role inside the nucleus too? with protons and neutrons.
It does. Now remember, the exclusion principle only applies between identical particles. So it applies between two protons or between two neutrons, but not between a proton and a neutron because they aren't identical.
Okay, so proton and neutron interactions are constrained by it.
Right. And this affects things like nuclear stability and how nucleons scatter off each other. For instance, Feynman mentions how the forces between nucleons are spin-dependent, and the exclusion principle influences which spin configurations are possible or stable for pairs of identical nucleons, contributing to the overall structure and binding energy of nuclei.
So even in the nucleus, the minus sign is shaping reality.
It really is.
Now, just to complete the picture, there's a fantastic macroscopic example of the boson's cooperative nature, liquid helium.
Ah, yes. Specifically, helium-4 atoms. The whole atom, with its two protons, two neutrons, and two electrons, has a total integer spin. So helium-4 atoms behave as bosons.
And at super low temperatures.
That n+1 enhancement factor just takes over completely.
Right.
As you cool liquid helium-4 down towards absolute zero, a huge fraction of the atoms don't just get cold, they start dropping into the exact same lowest energy quantum state, the state of zero momentum.
Billions and billions of atoms all doing the identical quantum thing.
Piling up cooperatively, just like the math says they should. And when you have a macroscopic number of particles all in the same quantum state, you get weirdness, you can see.
Superfluidity.
Superfluidity. The helium flows with zero viscosity, no friction at all. It can climb up walls, flow through microscopic cracks. It's a macroscopic quantum phenomenon, directly showing us the social nature of bosons.
Incredible. Okay, let's try and sum this up. It feels like we've seen how the entire universe, its light and its matter, is fundamentally shaped by one tiny choice.
Just a plus or a minus sign. When you exchange two identical particles, does the quantum amplitude stay the same, plus sign bosons? Or does it flip its sign, minus sign fermions?
And the bosons, the plus sign particles, are social. They enhance each other, leading to things like laser light, blackbody radiation, superfluidity.
While the fermions, the minus sign particles, are exclusive. They demand their own space, leading to the Pauli Exclusion Principle, the structure of atoms, the stability of matter, the diversity of chemistry.
It's profound. One simple sign rule dictates a fundamental texture of reality.
It really does.
So here's a final thought for you, the listener, to maybe ponder on your own, something Feynman himself flags. We sort of accept this rule. Particles are either bosons or fermions. It's either +1 or -1 upon exchange. That's just stated as a fundamental law of nature we observe.
But why? Why this dichotomy? Why only these two choices? Is there some deeper principle that forces nature to pick only plus or minus one? Or is this fundamental simplicity, this binary choice, just the way things are?
What are the implications when a rule this basic generates all the complexity we see? Something to think about.
Definitely food for thought.
Yeah.
Thank you for joining us on this deep dive into the strange world of identical particles.
We hope you enjoyed it, and we'll catch you on the next one.